right, guys, welcome back. Let's talk a little bit. Let me go to chapter 10 and talk about these three problems, if I could. Problem number 51, chapter 10, the Katz book. Now, again, I already lectured, or you'll find my lecture pertaining to chapters 10 and 11 in the Katz book, pertaining to momentum, collisions, and things of that nature. About momentum, conservation of momentum, collisions, that sort of thing. That's chapters 10 and 11. So I've already talked about that, so you might want to look at that. And again, you're not obligated to look at any of this stuff, guys. If you know what you're doing, go ahead and go for it. I would, for sure, be looking at the stuff in Canvas that I'm doing. I just think it's good stuff to check with, to check, see what you're doing the thing right. They are talking about a number of things here, guys. For number 51. Number 51, the space shuttle uses its thrusters. The space shuttle uses its thrusters with an exhaust velocity of 4,400 meters per second. That is the exhaust velocity, guys. 4,440 meters per second. The shuttle is initially at rest in space and accelerates to a final speed of 1 kilometer per second. It went from 0 kilometers per second to 1 kilometer per second. 1 kilometer per second is 1,000 meters per second. A, what percentage of the initial mass of the shuttle, including the full fuel tank, must be ejected to reach that speed? B, if the mass of the shuttle and fuel is initially 1.85 times 10 to the 6 kilograms, in other words, 1,850,000 kilograms, how much fuel is expelled to have this happen? Okay. We've said a lot. We are looking for the rocket going 0 kilometers per second or 0 meters per second initially, and then the rocket at the end is going 1 kilometer per second or 1,000 meters per second. The exhaust velocity, and my notes are a little more, pardon the play on words here, my notes are a little more exhaustive in Canvas sometimes, and it should be a little bit more here. But this is, velocity of the rocket at a point in time. These are the velocities of the rocket, velocity of the fuel, the velocity of the exhaust being expelled. We have done a few things. We remember the whole song and dance was basically based on something like this as far as force is concerned. We knew that M, the mass of the rocket at any particular time, that's not set in stone. This is variable, you guys. We're talking about rockets. That's a variable quantity. It's a variable quantity in that regard. We've done the whole song and dance when we're doing this thing. We've been here and we've done that. We've already. You saw me in the notes on chapters 10 and 11 regarding momentum and collisions and conservation of momentum. You saw me work it and get to here, and then we can do a whole lot of stuff here. You can multiply by the differential dt on each side. Multiply by the differential dt on each side and divide by capital M, and you get dVr. Multiply by dt on each side, divide by capital M, and you end up getting looking something like that at the end of the day there. Then you can do the appropriate integral. We've been there. This is MI, which is a lot, and this is MF, which is not a lot, just a little. And this is VRI, which happens to be 0, and this is VRF, which happens to be 1,000 meters per second. Okay, so we're here. You play the game here. Well, we don't need to deliver this speech again, guys. We've been here. We got VRI, when you actually do the integral, ln, the difference between the natural logarithms, which is the same as the logarithm of the quotient. You saw me do that in the notes pertaining to chapters 10 and 11. And if you divide by VE on each side, well, let's see here. Initial speed in this case, guys, was 0. We said the initial speed was 0. we got VRF equals negative VE top is small, bottom is big, the ratio is a fraction less than 1. The natural logarithm of a fraction less than 1 is a negative number. That's okay, because when I do the division here, it's a negative number, and these are just speeds. Gets confusing. I mean, there's a lot of ways to explain this. Multiply by negative 1 on each side, divide by VE, and we got MF, MI. All right, we're not really worried too much, guys. I mean, I could change, if I'm really hung up on this, there's a lot we can do here, but let us see what does work. They're in opposite directions to one another. Technically, they're in opposite directions, but both of these are positive right now. Throw a negative in front of it, positive divide by positive. See, we already kind of, so many ways to go, guys, but I guess for now, I'm not going to say it's easy. Just watch your step. Watch your step. What's negative? We already know this is going to be a negative number. This also has to be a negative number. You got to treat VRF and VRE and VE as magnitudes that are positive. Magnitudes are positive. The opposite of a positive number is negative. That's going to be a negative number too. No big deal. No big deal. You can play it a whole bunch of ways. Trying to argue how you could do it. Why don't you exponentiate each side? Put, this guy. And we know this is actually going to be a positive number. We're not maybe initially comfortable with that, but no, forgive me. Rather, this is the negative number right here, and this is going to be, so you're exponentiating each side. ln mf over mi. Exponentiate each side. Exponentiating the natural logarithm of this quantity gives me just this quantity. Exponentiating this is a good question, whatever it's going to be. Now they're asking they're asking a number of things here. I think they're trying to ask here, for this, they're trying to ask, what percentage of the initial mass of the shuttle, including the full fuel tank, must be ejected to reach that speed? What percent's got to reach that speed? Okay, I'll tell you what I'm going to do. There's a lot of ways to write this. I'm always a little on the apprehensive side on some of this stuff, man, when I want to discuss it. I'm not sure what's the best sometimes. I guess you can say, for this right here, is it true that delta M in its entirety is, delta M is the change in the change, MF minus MI over MF. MF minus MI over MF. Yeah, okay. Have the MF go into both places here. Actually, forgive me on that one. It's the right idea, but the wrong path. It's going to look really similar to this, but just forgive me on that one, guys. We caught it. This is the initial. The initial is the big one on the bottom. You start with MI. You end at MF. MI is bigger than MF. You write it like that. That's the same as delta M over MI. And what happens here is, you got it to here. That's what they want. They want they want a percentage. They want the percentage of mass expelled. This is the initial, this is the change. The change is MI minus MF over MI. May I ask you a question? Does MI go into MI? One time. Does MI go into MF? Yeah, sure does. That'll be your answer. If you can get it, that's going to be delta M over MI. 1 is 1. MF over MI. We did the song, we got it, we were here. We exponentiated this side, and we exponentiated that side. Here it is, we did it here. We did it here, and it got down to here. This is a fraction less than 1. These both got to be positive, and that's the negative right there. I'll make the long story short. The final rocket speed is 1,000 meters per second. The exhaust speed is 4,440 meters per second. If you evaluate this, you got it. You're done. If you evaluate this, you're done. Absolutely. Something less than 1. Let's see what we got here. It's going to come out to, well, let's take another, let's keep going. It comes out to 0.20166. Make that into a percent. It's about It's about 22.2%. 22.2% of the initial mass. 22.2% of the initial mass is exhausted, is ejected. 22.2% of what was the totality, the big number, the initial presence of mass, 22.2% of it was thrown out, was ejected in this process to get to where you got to go. It's that simple. It's that simple. What is delta M, they're saying? Still on 51 here, guys. Well, we've said a lot. Okay. Let's see what we could say here. They're asking here, what is delta M? Well, then we say that MI minus MF is delta M. Over MI here, that's delta M over MI. We said that was 22.2%. 0.20166. 0.20166 is that multiplied by MI on each side. They told us initially it's 1.85 times 10 to the 6 kilograms. Guys, you're just doing the mathematics at this point. If you get to here, multiply by mi on each side, put mi is equal to this. Delta M is 373,077.7 kilograms. Yeah, that's about 20% of what you initially had. It's a lot. It's a lot to go. And that's 51, A and B. Let's go to problem number 67. '67 is saying the position. Let me see what we got here. The position of a particle. The position of a particle of mass m1 equals 1 kilogram is described by the vector r1 vector equals the quantity 2t plus 5t squared I hat plus 4t j hat, where t is in seconds and our vector is in meters. The motion of a second particle of mass m2 is 2.50 kilograms, described by the vector r2 vector equals the quantity 3 minus 5t I hat plus the quantity negative t minus 2t squared j hat. A, B, C, what's it about? A, what is the vector position of the center of mass at t equals 3 seconds? B, what is the velocity of the center of mass at t equals 3 seconds? What is the total linear momentum of the system at t equals 3 seconds? So they're talking about this concept of center of mass. And I didn't go into it too much with the notes, but like I said, a lot of times this stuff gets flushed out when we do the problems themselves, you guys. So what we can say here for this one, and there's a lot here. Like the book does good coverage of it. There's a number of ways you can proceed on this whole thing, you guys, and and of course I have to, right, okay, we got that. Let's see what we do have. Okay, so basically, guys, they're saying a lot of stuff here. They're saying there's basically the position particle of the position of a particle of mass m1, which is 1 kilogram. It's a 1 kilogram mass, we'll call it m1, is described by a vector, r1 vector, and where t is seconds and r hat is in meters. The motion of a second particle of mass m2, which is 2.5 kilograms. The first one, m1 is 1 kilogram, m2 is 2 kilograms, is described by another vector, r2 vector. What is the vector position of the center of mass at time t equals 3, 0? What is the velocity of the center of mass at 3, 0? What is the total linear momentum of the system? Okay, so I don't know if how much I'm going to do. I showed a lot of ways to do it in the actual notes. I may refer you to Canvas on this one, but let me kind of see where I'm going to go here with this. There's a lot of ways you can go. So let's see what we can say here. What you would essentially do is you talk about two different places where something's located, and from here, you can do a number of things here. So let me exactly think what I'm going to try to say here on this one, guys. For this one, let's see, okay. Try to make a good argument as to what's going to get said. Apparently there's an easy way and a hard way on this. So you can look at the position vector that way. So what are they saying here, guys? They were saying, what is the position vector of the center of mass? Okay, I got, in the notes I kind of go in a number of directions. I got a feeling the second way I approach it is maybe one of the best ways to actually look at it. So I'll tell you what, this can get a little interesting, but let me see what I can say here. pick and choose how I want to do this one, guys. Second. All right, guys, let me 1 second here, guys. Okay, guys, let's keep going. Let's talk about problem number 67. Though I did not talk about center of mass when I did do the lecturing for, at least in one video for which I did the lecturing for chapters 10 and 11, one way or another, I mean, you gotta enter the dance somehow. So let's talk a little bit about what they mean by center, when we talk about the center of mass and other items. You know, the center of mass is kind of an interesting concept in its own right, I guess you could say. You can say basically the location of the center of mass is, so let's write this in a couple ways here. You can write this. The location of this thing called center of mass is all about a weighted average in a vector sense. It's 1 over capital M, which is the sum of all the masses that are considered. There may be n number of masses. M sub 1, M sub 2, M sub 3, M sub 4, M sub 5, plus ... plus M sub n. N masses, I add them together, I get capital M. That's what they mean by that. And this is the Greek letter sigma for summation so oftentimes in mathematics. M sub j, let's have, forgive me, M sub j, R sub j. Gets a little messy, but basically this is what they mean. In other words, if you're going to do a weighted average, you're going to take the mass of one of the elements and multiply it by its position vector away from some arbitrary origin of consideration. It doesn't matter where you choose the origin, actually. It'll work out the same either way. This stuff is independent of the coordinate system. Location is location. The numbers are going to change a bit, but it shouldn't. And there's ways you can actually prove that. Not our place right now to prove that, but we can actually prove that this is invariant under regardless of what coordinate system you choose in three-dimensional space. This could be three-dimensional space. Often we're using two-dimensional space just for convenience, at least from the standpoint of just teaching the material. But didn't we say that the three-dimensional space is really the most realistic way to deal with the forces, the momenta, the angular momenta, when we're talking about just trying to evaluate what's going on in terms of physics? Three-dimensional space is what we live in. Why not consider it that way in three-dimensional space? But anyway, this is the thing. You're going M times R repeatedly. You're adding them together, and then you're dividing by M. What happens is you get a new R. You get like an average value of R, a weighted average of where the center of mass is, where the location is. It does not matter where the coordinate system is vis-a-vis something like this. You can prove it pretty easily, actually. You can locate things apart from one another. You could put an R sub. I definitely do not want to do this. But we could say, well, that's the case here. We could locate something somewhere else. What is going on regarding that? So you could. It's something we can prove. We can't go into right now. You're gonna have to take my word on something like this, you guys. I will say this much: wouldn't the velocity of the center of mass, wasn't velocity the time derivative of the position vector? The time derivative of the position vector is, here's still a constant for you guys, summation. I usually use I, they use J, so let me stay with them using J. I think they went all the way to N on this one. Yeah, they did. M sub J, every one of these M sub J's is a constant. dr sub J, you're getting these right here, which is the same as each one of these is the sum of the velocity vectors. So it comes out something like this. M sub J, V sub J, for that particular V sub J. It's this guy right here. It's just nice to get this little weighted average because you can, if you're you can find out how the velocity of the center of mass behaves, and you got something looking like that. The acceleration of the center of mass would be dv center of mass dt, which is d squared r center of mass dt, the second derivative of the position vector, the second derivative of the position vector, or the second derivative of the position vector, or the first derivative of the velocity vector, and that ends up getting you. So there's a lot of games we can play here, guys. This is 1 over m. Forgive me, I'm not exactly thrilled with the chalk that I got right now, guys, but we'll figure out a way around that too. M sub j, every one of the m's is constant, just like 1 over big M is constant. Every one of the m sub j's is constant. This is going to be dvj vector dt. Absolutely it is, which is equal to 1 over m summation from j equals 1 to n, m sub j, that's a sub j. And you got this guy right here. We got that guy right there. So on and so forth. Well, I didn't do that when I first did the notes I gave you for chapter 10, chapter 11. Not that it wasn't important, but sometimes you got to pick your battles on that. I knew we were going to come back to this eventually. At some point, this stuff arises. Either you're obviously going to read it in the book anyway, but at some point we're probably going to, a good chance we see this stuff in some problem somewhere. Regardless to what level we're going to take the consideration of the problems. So we don't know exactly what great emphasis is going to be placed on exams and everything else regarding a center of mass type problem. At some point you're going to see it, either in the book or somewhere else in my notes. Well, you saw it just now. Here it is. So this is some of the stuff we're looking at. With that in mind, let's take those two masses and basically go down the line and play the game that's really outlined right here. So let's see what we got right here, guys. And I'll see if I can rustle up some more chalk of the chalk that I like a little bit better than what I have right now. But that's neither here nor there. We should be able to get through this okay. There's this problem and one more, and we'll kind of leave it at that for now. All right. Okay. Could have sworn I had more of the chalk I like, but let's use this a little bit. All right, guys, they're saying a couple things here. We kicked this around a little bit. let's use the data they gave us, and let's take this thing. Let's get this thing under control. Okay, let me just see if you guys can see that okay. Yeah, it's not too bad. Not too bad. All right, so we did this. We just did this. Let's do it again. Here it is for the record. Let's pay attention and play the game with the vectors that we got to play. Okay. Divide by big M, multiply by 1 over big M is the same as just dividing by big M. There's 2 items there. There's mass 1, location R1 vector, mass M2, location R2 vector. Mass M1 is 1 kilogram. The location vector is of interest. They are asking, all right, let's kind of be careful here. So when you do see what I'm about to do, it's not going to bother you too much. In fact, let's kind of cover ourselves. Let me write this down just on the side here so we can kind of play the game here the way it's supposed to be played. R1 vector is 2t plus 5t squared. Period. End of the story. That's true. R2 vector is 3 minus 5t I hat. Times the quantity negative t minus 2t squared. That's j hat. All right, maybe a little easier to look at that way. So they're asking you, this thing starts at t equals 0 and ends up going to t equals 3 seconds. They didn't even tell you where it started. They just want to know what's going on at t equals 3 seconds. What is the vector position of the center of mass? That's A. What is the velocity of the center of mass? That's B. And what is the total linear momentum of the system at 3 seconds? So they want position, velocity, and linear momentum, respectively, for ABC. Position, velocity, and linear momentum, all of the center of mass. That's A, B, and C, respectively. T equals 3 seconds. What happens here is, M1 is this. The total mass is a 1 kilogram mass and a 2.5 kilogram mass. That's 3.5. This guy right here, at 3 seconds, what is 3 squared? 3 squared is 9. 9 times 5 is 45. 3 times 2 is 6. 6 and 45 is 51. That's 51I. Try to give you guys some room. I'm trying to give you guys as much space to see this stuff as possible. Just in case. Put it right here, 3. What's 3 times 4? Got it. The other guys, too, remember now, it was M1 plus M2 is 1 kilogram plus 2.5 kilograms. Is everybody getting? That's where I get the 3.5 right here. Okay. I got the 2.5 kilogram right here. I'd like to see what the heck's going on. 2.5 kilograms, here we go. Put a 3 right here. 3 times 5 is 15. 3 minus 15 is negative 12. What do we got? Put a 3 here. Here's a 3, here's a 3. What's 3 squared? 9. 3 squared, 9. 2 times 9? 18. The opposite of 3 is negative 3. Negative 3 minus 18 is negative 21. Put the i's to, grind this out, man. Something associated with I, something associated with J. Something associated with I, something associated with J. Get all the i's together, get all the j's together, and then distribute the division of 3.5 throughout everybody and see where you are. Okay. Well, it's its own song and dance, I guess you could say. You end up getting, at the end of the day here, RCM. Okay, just forgive me again, guys. I want to make sure you guys can see okay. The lighting changes in here because I'm writing at a different time right now. It looks pretty good. Yeah, looks all right to me. Okay. So what do we got? Well, that's 51i. This is negative 30i. Negative 30i and positive 51i is 21i. This one right here is 12j, and this one right here is negative 52.5, something like that, I guess. Let me see. All right, maybe I got it wrong. Hold on here. This is 1 times 12j is 12j. This times this, yeah, I'm not going to take back what I said. It's negative 52.5. Negative 52.5 plus positive 12 is negative 40.5. The whole thing divided by 3.5. All right, it's quite the song and dance, guys. I'm not going to lie to you. 3.5 goes into here 6 times. That came out pretty nice. This goes into here. That's its own dynamic in its own right, right? Not quite. You're thinking it goes in here. Not quite 12, but it's going to be like 11 something. It's going to be negative 11.6. And this is in meters. So it looks pretty good. The location of it is fine. The speeds, everybody moves pretty nicely on this stuff, guys. There's not some of the I'd love to prove some of this stuff on a different level, but it's a question of how much time we have, and sometimes there's not a lot of it. So, but this is okay. This is this decent gut feeling for it, I guess. So that's RCM. It's about as simple as that. Now you could have, the way the whole thing, and that's it. I mean, we did it like that, and that's where it's at. We could have, so that's A. Let's just leave it at that. This is where A comes from. Now I could have drawn that same conclusion for A had I said, you know what? Let's take all this, and you see what we got right here, guys. Are we able to, let me kind of look at it another way here, guys, if you don't mind. You could have said, hey, look, guys, look, there's got to be another way to look at this. Well, first of all, that's the answer. End of the story. It's as simple as that. Could you have gotten there going like this. Let's take 1 and then go with this entire mess right here, and then plug in things as they go that way, as far as momentum and everything else is concerned. So you could say, man, there absolutely is no pretty way to do this. You could take this, the one that's there, and go 2t plus 5t. It's certainly not difficult, but it's like I said, there's no, and that's the I hat. And I'm going to leave the variables in there, guys. And this way I'll be able to do it. I'll always be able to do it. And the other one is 2.5. Let's see what we got here. I mean, it's going to be 2.5. Go 3 minus 5t. That's I hat. The other one, negative t minus 2t squared. J hat. Yeah, what an absolute mess. This is why I didn't initially do it that way. And then divide by big M, or multiply by 1 over big M. Well, big M is 1 plus 2.5. That's all this. You could go right here, and then this gives you kind of a moving tally of where the position vector is regarding the center of mass position vector as t proceeds. It's a lot here. I mean, there's definitely a lot here. If you actually did that, if you ground it all out, guys, so there's the answer for 1. This is the answer for 1. That's the end of the story. Wow. Are you telling me do this, go 1 times all this, go 2.5 times all that, and add all these together and get the new I? Then take the 1, go over here, that's a j here. Take the 2.5, go over here, that's a j over here. Add those 2 results and get a new j. When you're done with all that, divide by 2.5. If you actually do it, okay, let me just say it again in case this is not really clear. You take the mass, multiply across. Take the mass, multiply across. Add them together. You can only add like vectors with like vectors to simplify things. The I hats get added together, and after you go 1 times this, get an answer. You go 2.5 times that, get an answer. Add all of this and all of that, and you got a new I. Then take that right here, all of that, 1 times this, get all that. 2.5 times this, get all of that. There's a j quantity. Add the j's, get a new j from all that and all that. All this and all this give you a new I. All this and all that give you a new j. When you're done with that, you divide by 3.5. If you were to do that, our vector CM, now I'm going to leave it to you to do it. You gotta do it, carefully do it, and have the thing work out. But you've got RCM is 1.43 t squared minus 3t plus 2.14 j, I rather, plus negative 1.43 t squared plus 0.429 t plus j. It is absolutely a mess. That is the real abstract way of looking what RCM is. If you plug in t equals 3 seconds, if you plug in t equals 3 seconds right here, t equals 3 seconds right here, square it, multiply it by 1.43, minus the product, 3 times 3, because t is 3 seconds, plus 2.14, you'll get the I component of the RCM. If you do the same thing here, plug in the t right here, square it, the 3 square it times this, plus 0.429 times 3, you'll get the j component. I will promise you, if you do that, you will get the initial answer that I gave you within the last 5-10 minutes, whenever we had done it. When we got RCM vector is going to be 6i plus negative 11.6j. It's going to be in that ballpark in meters. Good enough for me. Now, if that's the case, how are we going to find this other stuff? Well, that's A. I mean, you plug in here, and you'll find what A is. We already found A. We said RCM. I showed you two ways. I showed you this way now. You plug it in there, you grind it out, you're going to get it. And that's your business. You're going to do that. You're going to check on that if you want to give yourself a little bit of practice regarding such matters. That's 6i plus negative 11.6 j. That's that one. Okay, we already said that, and I already said you can get that by just plugging in t equals 3 all the way across the board. You'll get this. They're asking for B, the velocity, and it is a mess. I mean, I'm not going to, nobody's lying to you on that one. So we got that. Let me just see here. We got here. If you take the derivative of all that, you take the derivative here, VCM, take the time derivative here, and you're going to get VCM vector is going to be dr CM vector dt. What the heck is that? Well, go ahead. Take the time derivative here. Bring the 2 down. It's going to be 2.86 t minus 3. That's nothing. So 2.86 t minus 3, that's I hat, plus negative 2.86 take the derivative, point and that's that. Good. Guess if I wanted to find acceleration, I would take another time derivative. Yeah, I sure would. Sure would. And it would be a constant acceleration, actually. There'd be no more t's. If you took another derivative, you took dVCM vector dt, you'll get ACM vector, and it'll be, bam, it'll be 2.86 I hat plus a negative 2.86 j hat. That's a constant acceleration going wherever it's going at a 45-degree angle from the x-axis is what it's doing somewhere on the lower part of it. It'd be in the, at that point, the fourth quadrant. But it'd be a constant acceleration. Well, nobody asked you. Nobody asked us, so we're not going to worry about it too much. So if that's the case, you guys, let's plug in t equals 3 right here and see what happens. You know, and that's going to be a whole bunch of ways to look at it. Just want to try to do some of this in my head. If you put a 3 right here, it'd be 3, 186, 42, 42 less than 600. It'd be 5.58. I'm thinking 5.58 I. So this VCM. Put a 3 right here and go for it. 5.58 I plus. Put a 3 right here and go for it. Now, it's not going to be quite as tame as the other one is, I guess, but this is going to come out to, yeah, it's looking good. And this one comes out to, so you got this guy right here, 5.58I and negative '" I just put T equals 3 in there and I got that guy. Sounds good to me. How do you want to find the momentum? Well, I could multiply by M, the center of mass, and take it that way. There's a bunch of ways I can go at this point, guys. Like I said, I don't like erasing this stuff generally when it's that convoluted of a problem, but you do have it. You do have a record of it, and you're going to be fine. See what we can say here. So that was B. There's an easy way and a hard way, I guess. The hard way would be multiply the center of mass. The momentum, the momentum vector of the center of mass will be the entire mass times VCM, like that. You can do it with the letters, you guys, with the symbolism. What's capital M again? It's 1 kilogram plus 2.5 kilograms. It's M1 plus M2. 1 kilogram plus 2.5 kilograms. 1 kilogram plus 2.5 kilograms is 3.5 kilograms. 3.5 times VCM, 3.5 right here, 3.5 right here, 3.5 here, 3.5 here, meaning 3.5 times each of those things I just touched. Multiply that across. Well, you know what? I already got it. I already got what the speed is. They gave us this. Now just multiply it by 3.5. So you say, if they already gave it to you, man, you got more than enough work to do. Yeah, you don't need, that's capital M. VCM at 3 seconds is 5.58. Grind that out, guys. Just multiply it out. And I got all of this in the notes. I mean, so if you can't, I just think you should, kind of just know the argument, I guess. At the end of the day, I get 28.5. And all of that is kilograms, meters per second. And that's what this is going to be. The momentum at that point. Kilograms, meters per second. This right here is meters, VCM. All of that at the end of the day is going to be meters per second. So kilograms times meters per second is going to be kilograms meters per second. And that is 67. It's actually easier explained if you're not writing it down, I guess. It's one of those things that's easier said than done. Neither one is really difficult, but writing it out and just keeping track of the alphabet soup, that can be a little challenging, but we can do it. We can do it. All right. That's 51 and 67. Let's go to 78. They're asking a couple things here, and I think we're okay. 78A and B, what are they talking about? They're giving you, there's two masses. One of them is of mass 4m. The other one's of mass m. M is the same. M equals m, obviously. One is 4 times more massive than the other. One mass is mass m. The other mass is mass 4m. There's a light spring, very light spring, that is attached to a block of mass 4m at rest on a frictionless horizontal table. A second block of mass m is now placed on the table in contact with the free end of the spring. And the two blocks are pushed together. When the blocks are released, the more massive block moves to the left. The more massive block moves to the left, the one that's 4 times more massive, moves to the left at 2.5 meters per second. What is the speed of the less massive block? That's A. B, if mass is 1 kilogram, what is the elastic potential energy of the system before it is released from rest? Well, for A, it's like that little kid that's standing on the ice with me. The ice is a meter thick, and the kid pushes me. The kid flies off. I fly off, but I'm 4 times more massive than the child, so I'm going to fly off at 1/4 the speed that the child is going to fly off. If the child flies off at 10 meters per second, I'm going to fly off at 2.5 meters per second, 1/4 the speed. Momentum is conserved there. Momentum is conserved in this situation. We should be okay on this, and then we'll see where they're trying to go here. We know that they're at rest initially. They're brought together, and bam, they're brought together. The spring is contracted. It's an ideal spring. They're brought together. Everybody's at rest. The kinetic energy is 0. Once you release the spring, all the spring's energy, all the spring's stored up energy goes into the two blocks. The two blocks fly apart. Their momentums are equal but opposite. So what does that mean? The sum of the two momentums, when you take sign into account, the sign of negative or positive, you add them together, you get 0. The initial momentum was 0, the final momentum is 0. Initial momentum is 0, the final momentum is 0. And how much and then they're asking here, in addition to that, what is the speed of the less massive block? We talked about that. What is the potential energy of the system before he's released from rest? We know the potential energy of the system. How do we know it? Whatever the kinetic energy of mass of one of the masses, and whatever the kinetic energy of the other mass, kinetic energy of the light mass and kinetic energy of mass with mass m and the kinetic energy of mass with mass 4m, if I find out those two kinetic energies and add them together, all of the spring's potential energy went into giving kinetic energy to those two masses. So if I add the two kinetic energies together, I got the potential energy. This is not that bad, guys. It should go pretty smoothly. Let's take a look at it. All right, guys, so I think it's pretty straightforward. When we read the stuff and do it, I think we're set. I think we're okay. Momentum initial equals momentum final. There ain't no momentum in the beginning because nobody's moving. Yeah, you put the spring together, but nobody's moving. There's going to be a negative and a positive, but we're going to just look at speed right now. That is true. I lighten it up by writing it like this, but I never forget. The rules are the rules. We're talking about vectors. At the end of the day, you better have that straight. Right here, we can kind of simplify if we know what we're doing. Initial momentum of the system is 0. It ain't moving. One guy, the big mass, is 4m. It takes off at v sub 4m. The other mass, m, takes off with speed small m. V small m, Vm. Mass times velocity, 4m times V sub 4m, the speed of the 4m guy. Mass times the speed of the small m. I just want to know how fast they're going. We're not going to get in big trouble with the other stuff. If one guy, we said the 4m guy went off to the left. The 4m guy went off to the left. At negative, well, we'll call the left negative. How's that? Negative 2.5. When everything went. The small m guy took off faster. Well, he's a lot smaller. It's going to be a positive number. He's going to the right. Let us see what is going on. 0 equals 4m v4m plus m vm. What do you say divide by small m on each side? One times Vm. Why don't you subtract 4 V4M on each side? 4V sub 4M on each side. Subtract 4V sub 4M on each side. So 1 times Vm is Vm. Negative 4, subtract, as we said, subtract 4 V sub 4M. Well, we just said the big one took off to the left at negative 2. Negative 4 times, I'm sorry, at negative 2.5. Negative 2.5 rather. Negative 4 times negative 2.5. So the big one took off to the left at negative 2.5 meters per second. Negative 2.5 times negative 4 is 10 meters per second. That's to the right. To the right. It's to the right, you guys. So we got that. That is A. That's A. B, well, there's no kinetic energy to begin with. The potential energy that's initially present is all going to get fired up and change the kinetic energy. All that potential energy is going to change the total kinetic energy of the system, is what it's going to do. So all that potential energy is going to change the kinetic energy of the system. What the kinetic energy of the system is, there was no kinetic energy to begin with. You got a final kinetic energy at the end of it. So the initial potential energy, there's no, that right there is KEF minus KEI. That's 0. This guy, what is it? Well, the spring is like this. Nobody told me how much they compressed the spring, so I got to take this thing as a whole. Yeah, that's true. That's true, but that's really what this is. That's the big picture. Nobody told me what K was. Nobody told me what X was, so I'm kind of in the dark there. For me to actually make a move on this thing and know what K is, they got to tell me how much they compressed it. What is X? What was X to compress it? Then I can find K. Or if I want to find X, they'd have to tell me what K is. If they don't tell me either one, it's kind of a fluid situation. I can kind of get a relation. There's certainly a relationship here, but I can't give specific answers unless I'm given a little more information. Well, either way, nobody really cares, guys. We're not worried about that. That right there is the potential energy. And the potential energy is going to be 1/2 the 4M, the big one, which is V4M, and the other one is I'm not done, but that's what I got to do. I got to find I got to find the kinetic energy of the 4m mass, and I got to find the kinetic energy of the 1m mass. You got to find the kinetic energy of each mass, add the kinetic energies together, and that's essentially what's going on, you guys. So, let's make the long story short, I guess you could say. Forgive the long distance here, guys, but here we are. I think they actually gave you the numbers on there. They said for this one, if M is 1 kilogram, what is the elastic potential energy of the system before it is released from rest? So it's 1 kilogram. If this guy's 1 kilogram, this guy's 4 times 1 kilogram, which is 4 kilograms. 1 kilogram, 4 kilograms, the quantity negative 2.5 squared, which is 6.25. The quantity 10 squared, which is 100, et cetera, et cetera. That's all you're doing. You're plugging in the numbers, guys. All right, guys. This problem was, I think we're in pretty good shape, even from a while ago on this one, but what the heck? We entered the dance. Let's go for it. You got 1/2 the 4m. 4 times 1 is 4. Then you go the quantity negative 2.5, or the speed, which is positive 2.5 squared. Doesn't matter. When you square it, it's not going to be an issue. The other guy's 1/2. It's 1. And it's 10 right here. And that's going to be squared. What's going on here? 1/2 of 4 is 2. The quantity negative 2.5 squared is positive 6.25. 2 times positive 6.25 is 12.5. 1/2 of 1 is 0.5. 10 squared is 100. 1/2 of 100 is 50. 62.5. 62.5 joules of total kinetic energy. That came from somewhere. It came from the potential energy that was stored in the spring. And that's it. That's some of the problem. A little bit more lecture on chapter 10 type material, chapter 10 and 11 type material, and here's some problems that we had done from there. All right, guys. Thank you for your time. We'll see you soon.